Assalamu alaikum. Let's continue part 2 in this chapter called Alkanes. Section 12.7 Properties of Alkanes, Organic Chemistry and the Curved Arrow Formalism. Organic chemists look at how and why reaction occur by examining the flow of electrons, and the flow of electrons is represented by a curved arrow. If it is in one direction, it's one electron, two directions, two electrons. The convention to show the movement from area of high electron density to one of lower electron density, the head of the arrow, the start of the arrow. It is important to get used to thinking of reactions as an electron flow. Section 12.8 Reactions of Alkanes. There are two general types of reactions. One is called combustion. The reaction of an alkane with oxygen is called combustion, an oxidation reaction that commonly takes place in a controlled manner in an engine or furnace. All combustion reactions are exothermic, which means heat is released, and all of them produce carbon dioxide and water, and they are spontaneous. When hydrocarbon combustion is incomplete, carbon monoxide and carbon containing soot are among the products. Carbon monoxide is a highly toxic and dangerous substance, especially because it has no odor and can easily go undetected. Breathing air that contains as less as 2% CO for only 1 hour can cause respiratory and nervous system damage or death. The supply of oxygen to the brain is cut off by carbon monoxide because it binds strongly to hemoglobin where oxygen is normally bound. Actually, the affinity of CO to hemoglobin is far more than the affinity of binding oxygen to hemoglobin. CO2 is non-toxic and because causes no harm except by suffocation when present in high concentration. The second type of reaction, called halogenation, is the replacement of an alkane hydrogen by a chlorine or bromine initiated by heat or light. Halogenation is used to prepare a number of key industrial solvents as well as other molecules that are used for the preparation of other larger organic molecules. In the halogenation reaction, as you can see here, only one hydrogen at a time is replaced. Here you see only one hydrogen is replaced at a time, and if allowed to react for a long enough time, all hydrogens will be replaced with halogens. So it depends on the presence of chlorine. So if we look here at halogenation, one hydrogen is replaced, then the second hydrogen, then the third hydrogen, then the fourth hydrogen. And all these are produced as mixture of products. It is not always necessary to balance the equation for an organic reaction as long as the reactant, the major product, and any necessary reagents and conditions are shown. In using this convention, it is customary to put reactants and reagents above the arrow and conditions, solvents, and catalysts below the arrow. Now, what about cycloalkanes? What is a cycloalkane? It's an alkane that contains a ring of carbon atoms. To form a closed ring requires an additional carbon-carbon bond and the loss of two hydrogen atoms. The general formula for cycloalkanes is CnH2n. If, for example, you have n equal 3 minimum, then n must equal 3 or larger. If it is 3, because you need a minimum 3 carbon atoms to form a triangle. So 3 times 2, 6. Compounds of ring sizes from 3 through 30 and beyond have been prepared in the lab. Now the carbon-carbon bond angles in cyclopropane are 60. This is the simplest cycloalkane called cyclopropane. All the angles are 60 and the bond angles in cyclobutane, however, this one are 90, much less than the ideal 109.5, that of a tetrahedral angle. These compounds are less stable and more reactive than other cycloalkanes. Even these two compounds are less stable and more reactive than other cycloalkanes. The carbon-carbon-carbon bond angles in cyclopentane and cyclohexane are near ideal. Both cyclopentane and cyclohexane rings are stable, and many naturally occurring and biochemically active compounds such as steroids contain such rings. Such as methanol, if you look at the structure of cholesterol, it has many rings, as we will see later. What are the properties of cycloalkanes? Cyclic and acyclic alkanes are similar in many of their properties. Cyclopropane and cyclobutane are gases at room temperature, whereas larger cycloalkanes are liquids or solids. Cycloalkanes are nonpolar, insoluble in water, and flammable. Because we said they are very unstable, they are flammable. Because of their cyclic structures, cycloalkane molecules are more rigid and less flexible than their open chain counterparts. If you compare propane, normal propane with cyclopropane, cyclopropane is more rigid and less flexible than normal propane. Rotation is not possible around the carbon-carbon bonds in cycloalkanes without breaking open the ring, whereas there is a free rotation in normal propane around carbon-carbon single bonds. Surprising uses of petroleum. Petroleum is a mixture of hydrocarbons of varying sizes. Petroleums work as a portable energy dense fuel and are the starting point of many industrial chemicals, makes it one of the world's most important commodities. 90% of vehicle fuel needs worldwide are being met by oil. In addition, 40% of total energy consumption in the United States is petroleum-based. Petrochemicals are chemical products derived specifically from petroleum and generally refer to those products that are not used for fuels. Now, when crude oil is refined and cracked, the primary petrochemicals obtained can be broken down into three categories. Alkenes, mainly ethylene, propylene, and butadiene. Ethylene and propylene are important sources of industrial chemicals and plastics. Aromatics, most important among these are benzene, toluene, and xylenes. These raw materials are used for making a variety of compounds, from dyes and synthetic detergents to plastics and synthetic fibers to pharmaceutical starting materials. So these aromatics are important in industry. Synthesis gas, a mixture of carbon monoxide and hydrogen used to make ammonia, which is used to make fertilizer, and methanol, which is used both as a solvent and feedback of other products. Now, numerous types of products are made from these petrochemicals, such as lubricants, like machine oils, motor oils, greases, paraffin waxes, synthetic rubber, plastics, petroleum jelly. Now, line structures are used almost exclusively in drawing cycloalkanes, with polygons used for the cyclic parts of the molecules. Remember here, this is a triangle. In organic chemistry, this is a compound called cyclopropane. A square in organic chemistry called cyclobutane. This shape, cyclopentane. 5-membered ring. 6-membered ring, cyclohexane. 7-membered ring, cycloheptane. 8-membered ring, cyclohexane. cyclohexane, and so on. So, cyclopropanes are named by putting the prefix cyclo in front of the parent name. For example, this consists of four carbons. For carbons in alkanes, it is butane. But because it is cyclic, it's called cyclobutane, and so on. So note these different structures. If we, for example, put here a substituent, for example, مثلا chlor or brom, then this is called bromocyclopropane. Chlorocyclopropane. If you put a methyl group, it's called methyl cyclopropane, and so on. Cycloalkanes are named by a straightforward extension of the rules for naming open chain alkanes. As I said, step 1, use the cycloalkane name as the parent. If there is only one substituent, as I said on the ring, it is not necessary to assign a number because all ring positions are identical. If we go back here, as I said, here if you put at any of these 6 positions, you put chlor, for example, this is called chlorocyclohexane. If you put the brom, it's called bromocyclohexane, and so on. Now, step 2, identify and number the substituents. Start numbering at the group that has alphabetical priority and proceed around the ring in the direction that gives the second substituent the lower possible number. If, for example, again we come here, we have here chlor, and here we have, for example, brom. So now you can number and give the alphabetical priority in numbering. The B in a brom before C. So you put number 1 here, 1, 2, and continue to 6. Then you can name this by the following: 1 bromo, 2 chloro, cyclohexane. If the two substituents are similar, for example, if here we have Cl and Cl, then you can put 1, 2 dichlorocyclohexane. You put the prefix di. If you have similar groups, you put di. If you have, for example, 3 similar groups, suppose you have chlor, chlor, chlor here, then this is called 1, 2, 3 trichlorocyclohexane. So start numbering at the group that has alphabetical priority, as I said, brom before chlor, and proceed around the ring in the direction that gives the second substituent the lower possible number. If we go back here, again, if you have here chlor and here brom, you start numbering 1, 2, 3, 4, 5, 6. Not from here 1, 2, 3, 4, 5, 6. To give the second substituent chlor small number. So you go 1, 2. So this is the end of this chapter 12, part 2. Thank you.